we studied in last lecture in 1 minute? Huh?
We studied the properties of the fluid, and we also did the continuum assumption.
Hmm.
We studied density, specific weight, specific volume, specific gravity, viscosity, and then we did some numericals on how much force we need to apply for the movement in velocity v.
So numericals, especially on viscosity, and I
Viscosity.
repeat, in last lecture itself, I said that one of the most important property in fluid mechanics is going to be viscosity, right? So
Yes.
moving further. So in today's class, we'll introduce the remaining properties like what is capillarity, surface tension, vapor pressure, and we will solve few numericals on based on all these concepts, right? And this will be the last lecture on properties of fluids. Next lecture, I am going to start the fluid statics. Clear? So moving further, I want you to solve a few more numericals on viscosity. Now take down this. Today actually I forgot my pen tab, so I'll be using a mouse to write on the screen. So let us see how it works. Okay. Anyway, take down numerical 1.3. The problem statement is a 25 mm diameter shaft is pulled through a cylindrical bearing as shown in the diagram. The lubricant that fills the 0.3 mm gap between the shaft and the bearing is an oil having a kinematic viscosity of 8 into 10 raised to power minus 4 meter square per second. Remember, kinematic viscosity is given and not dynamic. Right? And the oil has also a specific gravity of 0.91. So specific gravity of the oil is given, not density. I hope you know what is specific gravity. Now, determine the force P required. Now you can change the symbol if you want. So we are talking about the force. So if you want, just make it F, capital F for force. And here also you can write this as force F. So determine the force F, let us say required to pull the shaft at a velocity of 3 meter per second. Fine. Assume the velocity distribution in the gap is linear. Fine. So can you solve it on your own? Hello. Can you solve it on your own?
So can you revise one numerical?
Okay, see, look at the diagram. So you have a shaft like this, which is shown in the diagram. Some force F is applied and the shaft is pulled through this gap, right? And this gap is filled with oil. This is oil between your bearing and the shaft. Now this bearing, this part is stationary, and your shaft is pulled, right? See, the length of this sleeve is given 0.5 meter. This length 0.5 meter, right? So what is asked is what is the force required, force F required to pull this shaft at a speed or at a velocity of 3 meter per second. And they have said that assume the velocity distribution in the gap, this gap is linear, right? So you can say that this surface is fixed, the top one, and your this surface is moving with a velocity 3 meter per second now, right? Clear? So if you draw the velocity distribution in this gap, I'm just showing it here. So it will look like this. This part is fixed now. So you can say something like this type of velocity distribution, linear velocity distribution. So I am just exaggerating that part here. So it may look like this. So this is your velocity magnitude like this, and let us assume that this is the surface of your shaft at which the velocity will be whatever the velocity they have given, 3 meter per second. So linear velocity distribution. Fine. Now your job is to find out what is this force required. Is it clear? So find out. Now the idea is first you have to find out the stress, right? Shear stress, tau. So what you will do is you will use Newton's law of viscosity. Tau is equal to mu du by dy, right? Now I'll go to next slide. See, I'll be using this Newton's law of viscosity. Tau is equal to mu du by dy, du by dy, right? Now, if I want to use this expression, I must know what is mu. What is mu is dynamic viscosity. Now, dynamic viscosity is not given, but kinematic viscosity is given. So it is nu is, or you know the relation between these two, nu and mu, right? So kinematic viscosity, this nu is defined as mu by rho. You don't know the density of the fluid. Now, what should be the density of the fluid? What is given is specific gravity. Specific gravity of the oil, lubricating oil, is given 0.91, right? Hello, there is some background noise. Mute yourself. So the specific gravity of the oil is given 0.91. So you know that density will be, just multiply this by 1000. So you get the density of the oil as 910 kg per meter cube. So once you know the density, you put it here, and this is given kinematic viscosity. You can find out mu. So put this mu here. And now what is du by dy? So du by dy will be simply that velocity v divided by dy is nothing but the gap between your shaft and the sleeve. So let us call it as a b, the gap between sleeve and shaft. So you can put it here, and then you can find out the stress. Now once you know the stress, you can find out what is the force required to pull the plate. So the force required will be equal to, we know the definitions, stress is force per unit area, right? So force will be the stress tau multiplied by the area on which the stress acts, shear stress acts. Now what is the area? What is the area of that shaft which is in contact with the oil, and the shear stress is induced on that? So that area is pi d into length of the sleeve, which is I think given 0.5 meter, right? And diameter is 25 mm. So you can put that here and find out the force required, capital F. Is that clear? Hello. If you think this is simple, we'll go ahead. Hello. So tell me the final answer. What is the force required to pull that shaft at 3 meter per second? I hope you people are solving this, eh?
It's 285 Newton.
Very good. 285 or 286 Newton, right? Name yourself.
Manan.
Manan, very good. Okay, fine. Now, shall we go ahead? What about others? Are they getting same answer or something different? 286 Newton. Can I proceed further?
Yes.
Take down next. Now this is also pretty similar to what you did in numerical 1.3. So we have again the same kind of arrangement, that is shaft and sleeve. See, the dynamic viscosity of an oil used for lubrication between shaft and sleeve is 6 poise. Now remember, this time the dynamic viscosity is given, but the unit is poise. You know the relation between the poise and the SI unit, which is Newton second per meter square, right? So we have already noted down in last lecture that 1 Newton second per meter square is equal to 10 poise, right? So here we will convert this poise into Newton second per meter square. Now the diameter of the shaft is given 0.4 meter, and this time the RPM of the shaft is given 190 RPM. So let us call this as a capital N RPM of your shaft. Okay. Then what is asked? Calculate the power lost in the bearing for a sleeve length of 90 mm. The sleeve length is given 90 mm. So what will be the power lost due to this 90 mm length of the sleeve? That is what they have asked. And the thickness of the oil film, which is there between this gap of shaft and sleeve is given as 1.5. Right. Diameter of the shaft is given here. We have already noted down here 0.4 meter. Then find out simply the power lost in the bearing. Now to find out the power lost in the bearing, first of all you have to follow the same procedure. Find out the shear stress tau. Once you know shear stress, from that find out the force F. Then once you know the force, you can find out what is the torque applied. So the torque will be equal to the force F into the distance through which it is applied. So this distance will be half of the diameter of your shaft. So F into d by 2, this will be torque. Capital T stands for torque. Fine. And once you know the torque, then you can find out what is the power lost using the formula. You just note down. Power lost will be equal to this 2 pi NT whole divided by 60, where N is the RPM of the shaft, T is the torque, and power lost. Fine. Now the only missing part in this numerically is how to find out the tangential velocity of the shaft, which we called as capital V, or in few books you will find that the notation used is small u also for the peripheral velocity or tangential velocity. So u will be equal to, you might have used this formula previously, so it will be equal to pi d, diameter of the shaft, pi d n divided by 60. So this will give you the tangential velocity of the shaft, v or u, whatever notation you are using. So simply pi d n by 60, because RPM is given n. So remember, this should be in revolutions per minute because 60 is there in the denominator. So from this find out u, then use this u in shear stress formula, tau equal to mu du by dy. Then from tau find out F, from this force F find out the torque capital T, and from torque capital T find out the power lost in the friction. Fine. Is it clear? Solve it quickly. This kind of numericals may be asked in examination for 5 marks, not more than that. See, if you do not interact, I will not come to know whether you are really solving it or not. So it is difficult for me to judge whether you are attending the lecture or not. Again, it is difficult for me to judge whether you people understand the concepts or not. So keep on interacting in between.
So there is no use of length of the shaft, right, in this question.
Which length?
The shaft length, 90 millimeter.
90 millimeter is sleeve length, not shaft length.
Okay, yes, sleeve.
So this is your shaft. This one, huh? This one. This is your shaft. We have nothing to do with the shaft length. Reason being, the shaft length, which is what you can say, equal to the sleeve length, na? That is the only portion where we are talking about the shear stress. This one. इसके बाहर कुछ नहीं. Clear? So in examination, even if they give you the length of the shaft, something like let us say they give 120 mm, now you should not get confused. So you have to look at the length of the shaft, which is equal to the sleeve length, 90 mm, and not the entire length. Is it clear?
Yes, sir. So in this question, there is no use of the sleeve length also, 90 millimeter.
Sleeve length is not used. Why?
Because it's rotating.
So
I'm asking, like it.
So what?
There is no use.
I will find out the area A on which that shear stress acts. Where the shear stress is acting.
Okay.
You got it?
Yes, sir.
Very good. So tell me the final value. What is the power you are getting? This answer will be in watt, power. You can cross-check answer among yourself. Make it fast. It's very simple. See, what is the value of mu? It should be 0.6, right? Dynamic viscosity 0.6 Newton second per meter square, because 10 poise is equal to 1 Newton second per meter square. Hello. Is it over? See, with this speed, it is very, very difficult to finish the entire syllabus of fluid mechanics in 38 lectures.
Cross section, selection of cross section.
Is it 716 watt? Anyone getting 716 watt? Final answer?
Calculating.
Theories of failure मध्ये जास्त मी बाकी सगळे घेतलेले आहे, पण मी हा MSST फक्त डिटेल
I am assuming this class is faster compared to B division. No?
Basically, sharing मध्ये standardization.
Yes, sir. 716.3.
Very good. So it is close to 716 watt. That's it. So what you understood from these two numericals is how to find out the power lost or how to find out the force required to pull the shaft. Both things you have calculated. Now these four numericals are more than enough on viscosity. Now we'll move further and we will talk about another property of fluid like surface tension and capillarity. So what is your understanding about surface tension? You must have studied in physics, right? What do you mean by surface tension? What is surface tension? You may be knowing, but you are not in position to, what you can say, express in terms of definition. But you may be knowing the concept, I'm sure. So the surface tension, now I'm going to represent the surface tension using the symbol sigma, Greek symbol sigma. So the surface tension coefficient sigma can be defined as the intensity of intermolecular traction. So this is important word. Intensity of intermolecular traction per unit length along the free surface of the fluid. So in short, you can say the surface tension is nothing but the surface tensile force per unit length. I said surface tension force or surface tensile force per unit length of the surface. You can call it as the surface tension. What is the unit of surface tension? Sigma. So it is simply given in terms of Newton per meter because it is force per unit length. Force in Newton and per unit length in Newton. As simple as that. Right? So you have seen the fluids have the, what you can say, the surface which is under tension all the time, right? It acts like a thin film which is stretched, right? Now why this is happening? Because of the surface tensile force or surface tension. So you know the concept very well. Now why the surface tension occur? So the reason is the unbalanced cohesion forces which are present at the surfaces, and they produce the net downward force which acts in the what you can say which acts through the surface in the downward direction, right? And that's the reason why that film looks like a stretched membrane, thin membrane, right? So the concept of surface tension. Now on screen I am going to project what you can say the two surfaces where, or the two cases where either there is rise of the fluid in the tube or there is drop of the liquid level in the tube. So we know that effect because of the surface tension we call it as a capillarity effect, right? So I hope you may be knowing capillarity, right? Okay. Now, what are the parameters on which the surface tension or surface tensile force depends? So it basically depends on the temperature, and it also depends on the type of the solid interface. Means whether your liquid is in contact with the glass or a liquid is in contact with any other material like wood, or a liquid is in contact with any other metal, right? So it depends on the characteristic of your material as well. Fine, and of course the temperature of the fluid. Fine. Now, this is just one example given. You know, this for a drop of water on a glass surface, will have a different sigma surface tension from the similar amount of water on the wood surface. I just now explained that it depends on the surface tensile force. So it is always in connection with the surface in which your fluid is in contact, surface tensile force. Fine. Moving further, see, we know this. What is weighted area, non-weighted area? You have already studied in physics, 11th physics. So I am not going in much details of this. However, I want you to use this concept for solving the real life situations using the concept of surface tension. Right now, look at this diagram. So this diagram depicts the capillary rise in a tube. So when I have a small diameter tube which I am dipping through the surface, then there is the rise in the liquid level in this tube. We call it as a capillarity action, right? So what is acting at this surface, free surface, is the surface tensile force. So I am just showing it here. So it will be like this, and this is nothing but our surface tension sigma. This component is sigma, and the sigma is acting the, what you can say, the angle made by the sigma with the vertical. This angle is theta. We know this, right? and h is the height of the column, which is from the free surface. So this will be free surface, height of the liquid column. So this is typical. For example, you have a glass tube dipped in water, so you will get this type of configuration, capillary rise. So we call this as a capillary rise. Fine. Now how to analyze this situation? Now why there is a rise of water in this tube? Bolo. Why there is rise of water? Let us call this 2r as capital D also. So diameter of the tube, let us say this one. Why the liquid will rise in the tube? So of course that is because of the surface tension. We know this, right? So based on your understanding of the concept of capillarity, derive an expression for the capillary rise in this case. Derive an expression for this H. Can you derive on your own expression for H, capillary rise? Can you derive the expression? If it is possible, say yes, otherwise hello. Hello. Can you derive the expression for capillary rise?
No, sir.
No.
No, sir.
How it is? You must have studied in physics, no, or not? Okay. You will just note down one statement and then you start deriving the expression. So write down that statement. I have not written on the slide, so you have to note it down. See, the statement is the vertical component of the surface tensile force. Write down the vertical component of the surface tensile force is balanced by weight of the liquid column. The vertical component of the surface tensile force is balanced by weight of the liquid column. Now I am going to just show the free body diagram for this situation. Force balance I am going to show here. Now look at this. So I am just taking this surface here, and this is our sigma, the surface tension, right? And this surface tension is acting at the circumference, right? So that's why I am multiplying this by this 2 pi r. So sigma into 2 pi r, this whole component will give me the surface tensile force, right? So if you are not comfortable with the symbol r, I would suggest you go with the symbol d, diameter of the tube. So you can simply write this as the sigma surface tension multiplied by pi into d, circumference pi into d on which it acts, right? Sigma into pi d, right? And this force, vertical component of this force, is balanced by the weight of the column. So this is your liquid column. So weight of the liquid column, how we can say the W is, we can find out weight of the liquid column, right? W. So these two are balanced. So this is simply the sigma pi d, the surface tensile force acting at angle theta. So its vertical component will be sigma into pi d cos theta. Cos theta. So this must be balanced by the weight of the column. Now what is the weight of the column? I will find out weight of the column. So it will be simply rho g into the volume of the column, rho g v. So rho g is what? Specific weight. So this one, gamma. So this rho g into volume of this column. Now what will be the volume of the column? So it will be, I am writing in terms of diameter. So it will be pi by 4 d square cross section area into height of the column. So this will give me the volume of the column, right? So when you solve this, expression, finally you will get the expression for the capillary rise, which will be 4 sigma cos theta divided by rho g into d. So this is the expression for capillary rise in this case. Is it clear? So in single line I said the vertical component of the surface tensile force will balance the weight of the liquid column in case of capillary rise. So this is weight of the liquid column, which is balanced by the vertical component of surface tensile force. So sigma into pi d cos theta is the vertical component of the surface tensile force. Is it clear? Now on similar lines, can you find out what will be the capillary fall for this case? Let us say that you have the mercury here and you are dipping this tube inside the mercury. So we know that there will be the capillary fall. Right. And similarly, I can show the surface tensile force at this location. So this is going to be a sigma. Right. This is your sigma. And the angle made with the vertical, this angle is going to be theta. You see the direction of theta measured is clockwise. You will see this angle more than 90 degrees. Right. Now, in case of capillary fall, how you will write the force balance at this particular point, let us say. So the vertical component, again, vertical component of surface tensile force is balanced by now. There is no height of the liquid column here, no? But what is acting at this point is, see the pressure is acting on this surface. Pressure is acting everywhere, right? I am just showing it for the what you can say understanding purpose here. Pressure. So what I can write is the pressure force exerted at this level. Pressure force is balanced by the vertical component of surface tensile force. Fine. So when you write the expression, this component left hand side will remain as it is for this case also, and the right hand side here we are going to write the pressure force. Now when you write pressure force, pressure is simply given as in static fluid. Timing, you just note on this, is given as rho g into the height of the column. We are going to derive this formula in next module, not just next module, maybe in coming 2-3 lectures we'll derive this. Pressure in a static fluid is given as pressure as rho g h, right? And the pressure force will be rho g h pressure into the area on which it acts. So the area on which it acts is this area, which is pi by 4 d square. So for capillary fall, you will equate this expression with this rho g h into pi by 4 d square. So this should be P into A, pressure into area on which it acts. That will give you force. P is only pressure. So when you balance these two forces, again you will end up getting the same expression. Again you will get the same expression for the capillary fall, H as 4 sigma cos theta upon rho GD. Only thing is here, theta is more than 90 degrees. So this cos theta will be minus. So that indicates that there is capillary fall and not the rise. In case of mercury, you will observe this type of situation. Is it clear how we derived the expression for capillary rise and capillary fall?
Yes, sir.
Now can I go ahead?
Yes, sir.
Fine. Now what we'll do is we'll try to analyze the situation where we'll take a liquid droplet. We'll cut the droplet into 2 equal halves and then we'll find out surface tension in that case. Imagine the situation, we have a liquid droplet which is cut like this. So I'm just showing the free body diagram for the maybe the right half of your droplet. Fine. Now we know the surface tension will act at this periphery, right, which is shown in the diagram, sigma, right? And r is the radius of your droplet. So let us talk in terms of the diameter of the droplet, capital D. Fine. Now when you cut the droplet and under equilibrium write the force balance, that time you should remember that the surface tensile force must be balanced by the pressure force. Now, what is this pressure force? Pressure delta P, change in pressure, multiplied by the area on which it acts, right? So assume that there is some external pressure, let us say PE from the outside, and there is inside pressure within the droplet. We'll call it as a PI. So this PI minus PE is nothing but your delta P. So the change in pressure, delta P. So delta P into area on which it acts. So this force must be balanced by the surface tensile force. Now what is surface tensile force? Sigma is the surface tension. So sigma multiplied by this circumference on which it acts, let us call it as pi d, right? So this must be balanced by this force, pressure force. So we are writing it as delta P, delta P. Now instead of writing in terms of R, I will write pi by 4 d square, capital D, let us say d square. Fine. Now forget about this. So this is simply the force balance I am writing for this liquid droplet. Now remember, when I cut the liquid droplet, inside it is solid, right? So there is only one surface on which the surface tensile force is acting, right? So what will be the situation if I cut a hollow bubble like this? So in case of hollow bubble, you will observe there are two surfaces which are in contact. The inner surface of the bubble as well as outer surface of the bubble. So the surface on which the surface tensile force acts, this side must be multiplied by 2 in that case. Is it clear? Because there will be two surfaces, two such surfaces, pi d, on which this surface tension is acting. Clear? So when you write this force balance, what is the expression for delta P you get? That I am going to project it on the screen now. Huh? So all this I already explained, so I am keeping it for your reference. Later on you can go through this, but I explained this. Now, so I am writing the force balance. This is written using R, and this I have written using the diameter d of the droplet. So at the end I get delta P is Pi minus P is 2 sigma upon R, or in terms of diameter it will be 4 sigma by D. 4 sigma by D. Right. So this is for liquid droplet. Now, if I follow the same kind of analysis for a hollow bubble, so I have to multiply this side by 2. So this will be added. Then what I get is, instead of 2 sigma, it will be 4 sigma by R, which is also equal to 8 sigma by D, capital D. So this will be the expression for delta P in case of hollow bubble. Is it clear? So if I take, let us say, a liquid jet like this, liquid jet this way, and if I cut it from the center, and if I draw the free body diagram for the half of this jet, let us say diameter of the jet is capital D, and this length of the jet is L, capital L. Then in that case, following the similar analysis, I can find out what is delta P. So it will be for the liquid jet, the expression should be pressure. This delta P should be equal to 2 sigma by D. So just note it down and try to find out at your end later on. So for liquid droplet, this delta P is 4 sigma by D. For hollow bubble, it is 8 sigma by D, and for a liquid jet, it is 2 sigma by D. So the last derivation I leave it to you. Is it clear? Now, coming back to, if you refer any Indian author book, what you will observe is they have not written delta P. Instead of delta P, they simply write P. Now the idea behind doing this is, what is this delta P? It is Pi minus PE. Pi minus P, inside pressure minus external pressure, right? So in most of the books, Indian author books, they assume that this pressure is going to be the atmospheric pressure, right? So if you take this as atmospheric pressure, then by default delta P can be replaced by simply P. That is what the convention they have used. However, the conceptually both things are right. You need not have to get confused out of it. Is it clear how we derived the expression for this delta P? In case of liquid droplet, then hollow bubble and the liquid jet. Now can I go ahead?
Yes.
Okay, fine. Now based on whatever we have learned up till now, the capillary and surface tension, I want you to solve these numericals. See, next we have 15 minutes. Now we should be in position to solve 4 numericals in next 15 minutes. Take down first numerical 1.5. Derive an expression for the capillary height change H for a fluid of surface tension sigma and contact angle theta between two vertical plates a distance capital W apart as shown in the diagram. What will be the H, height of the column, for water at 20 degrees centigrade if W is equal to 0.5 mm. So for water I should mention what is the sigma surface tension for water and the air interface. So that value I will write on the screen, and then you can take it for calculation purpose. So note down sigma should be 0.073 Newton per meter for air water interface, fine. Can you solve this? So this dimension is W, the gap between these two parallel plates, You can assume the dimension, another dimension, that is the width of the plate normal to the plane of the paper. If you want to assume it as small b, width of the plates, and height of the column is h, angle is theta. So as they are given water air interface, you can simply say theta will be equal to 0 for air water interface, we know. And we also know what is theta for the mercury glass interface, mercury air interface. कितना रहता है mercury के लिए? You must have studied in physics, no? Or not? बराबर है? Hello.
Yes, sir.
So now find out the capillary rise between the gap of these two parallel plates. So which concept you will use? The vertical component of the surface tensile force must be balanced by weight of the liquid column. बस यही use करना, बाकी कुछ नहीं है उसमें. It's very simple. Are you solving it or not? So the reason they have not mentioned anything about width of the plate is in the calculation this will get eliminated automatically, this width of the plate. Okay, so what is the vertical component of surface tensile force? So the surface tension will be acting, sigma will be acting at this place, right? I'm just showing it like this, sigma, fine. So this angle is theta. So you can say the vertical component will be, what is the vertical component? Sigma cos theta, right? Multiplied by, now the length on which this surface tension acts. What is the length? So it will be this length एक B हो गया, and on this side there is one more B, right? So on this surface, the surface tension is acting now. So you have two such lengths, one from this side and another on this side. So you have to multiply the sigma cos theta by the 2 into B, right? This must be balanced by the weight of the liquid column. Now what is the weight of the liquid column? It is, we already noted down, I guess. Weight is given as rho g into volume, volume of the column. So rho g multiplied by volume of the column will be, this is your rectangle, right? And just expand it in the B direction like this, right? Getting me or not? So what is the volume of this? So it will be this capital W, this dimension, multiplied by the plate width B multiplied by height of the column H. So this will give you volume, right? Note down, this is width and not weight, capital W. Or if you are not comfortable, just replace this W by any other notation. And when you solve this, if you assume theta equal to 0 for water air interface, then at the end you will get the expression for H as 2 sigma divided by rho g into this W, gap between the plates, W. Is it clear? VB will get cancelled out throughout, or not? Hello?
So H is 0.015.
H is
0.015
0.015 or
meter.
is it? Any other answer? Or is it 0.3 meter? 0.03 meter?
Yes, sir, 0.029.
Ah.
Yes, I forgot to.
So, you forgot to multiply by 2, remember. So the answer, final answer is 0.03 meter, right? See, getting 0.03 meter in this numerical is not the important part. Important part is how to balance the force and how to arrive at this expression. This is important. उसके बाद तो क्या calculation है? I hope you understood how we did this. Now can I go to next slide?
सर आई हैड अ डाउट.
हाँ पूछो.
सर हम लोग ने 2 भी लिया, लेकिन हम लोग को पूरा पेरीमीटर का लेना पड़ेगा ना रेक्टेंगल का.
No. See, here surface tension is not acting on this surface, no? It is acting on this.
Okay.
So don't be under impression, surface tension is acting on this. No, it is not acting here. It is acting here. These two sides. Now can I go to next slide? Take down numerical 1.6. Now you just understand what this numerical is all about, and I leave it to you to derive expression for what is asked, the capillary rise. I leave it to you. Now again, same concept you will use here. So we have the two concentric tubes having the radius Ri and Ro, and these two concentric tubes are dipped in the water, and then there is a rise in the liquid level in the gap between these two tubes. Is it clear? A rise in the gap between the two tubes. and your job is to find out what will be the expression for H capillary rise. Now again, which concept you will use? The same concept. The vertical component of the surface tensile force is balanced by the weight of the liquid column. Follow the same procedure and you will be in position to find out the expression for capillary rise. So this I leave it to you as a homework. You can do it at your end. Fine. Now next, take down 1.7. So a water bug is suspended on the surface of a pond by surface tension. Water does not weight the legs of this bug. The bug has 6 legs and each leg is in contact with the water over a length of 5 mm, which is shown in the diagram. 5 mm length जितना surface contact में है leg का, ठीक है? Then what is the maximum mass in grams of the bug if it is to avoid sinking? So you have to make sure that this bug will not sink in the water. So you have to find out what should be the weight of this bug. Take surface tension of water as this, you have already noted down. So take down this value sigma, surface tension of water, and find out what should be the weight of this bug or mass they have said. So small m, mass of bug you have to find out. Okay. So if I show the side view of this leg of this bug, it may look like this, right? Take it as a something like a cylindrical surface, and the water will be surrounding like this, right? Okay. And at this end there will be the surface tension sigma, right? Is it clear? And the weight of the bug will be divided on these 6 legs, right? So let us take this as a weight. Fine. I am just showing it for the 1 leg. You can do the calculation considering 6 legs of the bug. Now again here also we are following the same concept, that the vertical component of the surface tensile force must be balanced by the weight of this bug itself. Then and then only bug will float, otherwise it will sink, no? Are you getting my point or not? So what is the vertical component of this surface tensile force now? Bolo. See, considering the water air interface, theta you can consider it as a 0. Huh? Theta can be considered as 0. So instead of writing sigma cos theta, straight away I am writing sigma. Okay. Now the sigma, there are 2 sides which are in contact with the water. So for 1 leg, I will take this as 2 sigma, right? For 1 leg, and we have this 2 sigma multiplied by the length. Let us call it as small l. So 2 sigma into L is the surface tensile force for 1 leg, and we have 6 such legs, right? So this is the vertical component of surface tensile force. This must be balanced by the weight of your bug. So weight of the bug, which is mass of the bug multiplied by g, acceleration due to gravity, right? So now remember that sigma is given, length which is in contact is also given, and this is 6, not sigma, this is sigma, and g you can take. हाँ बोलो
2 सिग्मा लिया क्योंकि लेग के दोनों साइड टेंशन
हाँ, यहाँ पे देखो, यहाँ पे ये ऐसा अगर मैं थर्ड इसमें दिखाऊंगा ना डायरेक्शन में, तो ये दोनों रहेगा ना. So that's why we are taking 2 sigma per leg, and L is length which is in contact. ठीक है? And ये 6 किस लिए है? Because 6 legs are there. So So 6 such cylinders will be in contact. This is what we are assuming. So what is the mass of the bug now? In grams, huh? Make it fast.
Zero 0.45.
Very good. It will be around 0.446 gram. Huh? Fine. See, in this numerical, what is important is understanding the concept. Calculation is secondary. Our focus, or at least my focus, is on the concepts behind. And I repeat, the same concept we have applied here. What is the concept? The vertical component of the surface tensile force is balanced by weight of the bug. Now, last one. This numerical I leave it to you. You can do it on your own, and if not, I will provide the solution in our class material. Right? So the problem is we have a blade. In first part, we have a double-edged blade. So there is the edge on both sides of this blade, and whose weight is given, and the total length which is in contact is also given, 206 mm, right? And what is asked is find out this theta angle theta made by the surface tension force in such a way that the equilibrium is attained. So to maintain equilibrium, what should be the value of theta? This is what they have asked. Fine. And in second half, what they did is they replaced this blade, double-edged blade, by a single-edged blade, and whose again weight is this mass is given. Then the total length which is in contact is also given. It is, I think, it is half of this only. No, not half of this. So one side is removed. Then they have asked, explain why this blade will sink. Second blade will sink, and will the surface tension will not support this single edge blade. And you have to support your answer with justification by calculation. Calculation से दिखाना है तुमको कि वो blade sink हो जाएगा. It means you have to prove by calculation that the weight of the blade is more than the surface tension or surface tensile force. Then there is no question of floating of this blade on the surface. But you have to prove it by calculation. That's it. I think we are again running out of time, and now I declare our properties of fluid part is over. Is it okay?
Okay, sir.
Very good. So next lecture I am going to start fluid statics part. Just wait.